Welcome to the world of moving water, everybody. So we're coming out of lakes and getting into streams and rivers. First, what I want to say is that when we're talking about a stream, a river, a creek, a great river, essentially I don't care about those words because trying to define what's the difference between a creek and a stream and a river and a great river is pointless. Let's just call it lotic water. That's L-O-T-I-C. That means moving water. Let me write that down here. So lotic is just flowing water, right? So we're going to be talking about fluvial ecosystems, and we're talking about water that runs downhill, right? So let's not talk about these big differences between, these words that blend together. Now, one of the most important things about any type of fluvial ecosystem is its watershed. Another word for that is catchment or drainage basin. So essentially what that is at any one point, so we've got this little red dot here, the watershed then is all of the land that drains into that one spot in the river. They're nested within each other and hierarchical. So something that happens in this tiny little watershed can affect the bigger watershed, but they have a bunch of smaller things adding up to the whole bigger watershed, and that will change what's going on in the river. So one of the most commonly measured things about rivers is people want to know how big the river is. Okay, so stream size can be measured in lots of different ways. Now, the Strahler stream order is one way to do that. And what the Strahler stream order does is it takes, so right here is the point where water is permanently flowing. Okay, so you'll have an ephemeral stream, above it maybe that water is flowing some of the year, but at this point it's flowing permanently. So we call that a first order stream. So we put a little 1 there. Okay, now to get a second order stream, what you need to do is it has to meet with another first order stream, so it gets 2. However, if a tributary of first order runs into that second order stream, it still stays a number 2, a second order. So it doesn't turn into a third order stream until it meets another 2. So here we have actually 3 2s all meeting in the same spot, but so all that does is makes a 3. So over here then we have 1 1 1 1. So so this is a 2, this is a 2, this is a 3. So then you have 2 3s coming together and you get a 4. Now what this does then is it makes it harder to get bigger numbers, right? The Mississippi is only a 10th order stream. But there's some problems. Well, first I should say, the Amazon is only I think it's either 12th or 13th order stream. So even though the Amazon is much, much, much bigger than the Mississippi, its order isn't that much bigger. The thing is, there's a decent amount of problems with the Strahler stream order, right? So if you look at, let's say this watershed, let's say there's a watershed that's, kind of like something like that, and, comparing it to this watershed that's, say like that, right? Now, the type of watershed over here on the right could be created in a gorge or a steep valley, right? Where basically you have a bunch of first order streams coming in to make a second order stream. So up here, this is a second order stream, but because all of these first order streams are coming into it, it's at the bottom is a second order stream. So think about how much water is flowing through at this point when it was a second order stream, and how much more water it would have flowing through at this point when it's still a second order stream, right? So this second order stream is not going to be equivalent to that second order stream, right? The little tiny sub watershed that would make this second order stream is only that big, whereas over here this is a pretty big watershed. So Strailer stream order is a way to measure stream size. It's not great, but it's one of the ways that we have. So think about this. Put the video on pause and try to figure out what that purple stream, what order that is. Okay, I'll reveal the answer in 3, 2, 1. All right, it's a third order stream, right? So we got 1, 1, 1, 1 here. So all of these is leading up to a 2. And then, so the 2's come together to get a 3. And this first order coming in here doesn't do anything. It keeps it a 3. What we see is Strailer stream order is roughly correlated with discharge. What is discharge? That's the amount of water flowing down the river. And this is given as a volume per unit time. So oftentimes with scientific things, we say cubic meters per second. If you work for the EPA or the Army Corps of Engineers, you'll use cubic feet per second. But like Australia uses weird like acre feet per hour or something. Yeah, doesn't really make any sense. But so cubic meters per second is what we're kind of looking for here. So generally, the higher the number, the higher the stream order, the more water is going to be flowing down that stream, and that's not necessarily surprising. How do we measure then discharge? Discharge is estimated by area times velocity. Okay, so don't look at this yet, but what you do is you find the cross-section of the stream, the area of the cross-section of the stream, okay? And you can do this very simply by using average depth and average width. So average width is 4 meters, average depth is 2 meters, so you get a area of 8 meters. Now there's other ways to measure the area of the stream. So let's say your stream bed were to look something like this. Generally what you would do is you would chop the stream up. Let's pretend these lines are vertical. Chop this stream up into a bunch of different sections. Measure these, all these widths would be equal widths essentially. So those would be the same. And then you could measure the depth in the middle of each one of these sections to figure out the depth, and then you would make these into like little rectangles, and you could figure out the area that way. Then what you have to do is you put a flow meter in the middle, either in this case it'll be in the middle of the river, and we find out that water is moving at 2 meters per second. That's actually really fast, but it does happen. It wouldn't happen in a stream that's only 8 square meters wide. But so what you do is you take that 8 times the 2 and you get 16 cubic meters per second. Okay. Now that's the way we generally do it. If you do it here, you would basically take a measurement of how fast the water is flowing at each one of these little rectangles, and then multiply. Basically, you'd find the discharge of just this tiny little thing added to the discharge of this rectangle, added to the discharge of the next one, next one, next one, next one, and so forth. Okay. Another way to figure out discharge is to use something called a weir, right? So this little dam here with this notch taken out is a weir, and what you do is essentially take a little bucket, put that bucket there, and then let's say it's a cubic meter bucket, and you time how long it takes for the river to fill up that bucket. So you would get, and then you just divide that to get the cubic meters per second. You would just take the time divided by how many seconds, and you would figure out how many cubic meters per second is coming through, right? Very simple way. The thing is, what weirs do allow you to do is, because this is a known this little notch here, because this notch is a known like size, when the water is at this level, we know that you basically calibrate it. You go out and put that bucket underneath and see how long it takes for that bucket to fill up. Okay, this is a metaphorical bucket. obviously, or it'd have to be pretty big. But what you can do is basically calibrate it at each given height. Okay, so let me draw that again, maybe over here. So here's your weir, and because you know basically what the discharge is at this point, what the discharge is at this point, maybe here it's 2 cubic meters per second, and here it's 8 cubic meters per second. All you basically have to do then is go out and look to see where the water is and what level it's at, and you'll know what the discharge is, because this weir then is essentially calibrated. And that's one way that we can, another way we can measure stream discharge. Now, discharge, as you might imagine, is roughly correlated with watershed area, right? So if you were to draw a little graph and you look at area and discharge, which is often abbreviated as Q, you would expect, something that's looking like this. That basically, the bigger the area that is collecting water, the more that will drain into it, okay? The thing is that the Ohio River is right here, at this point right here, the Ohio River has a discharge of 7,000 cubic meters per second, okay? Now compare that to the Missouri River, right? Now, the Missouri River is a much bigger watershed, right? So what happens when the Missouri River dumps into the Mississippi? What is the discharge of the Mississippi, or the Missouri River there? And the answer is much less. It's 2,400, okay? So why is this one 2,400 where this one is 7,400, right? And the answer is, it's just, this is the Missouri River Basin here is a relatively arid area, right? This is all short and tall grass prairie, where this is deciduous forest, and there's just more rain over here. So you have to be careful when looking at this here, where the Ohio River might kind of be up here and the Missouri River would be down there. So there is some error here. Right, let's define a little bit about the river and the floodplain. Okay, so underlying pretty much most rivers, not all rivers have bedrock necessarily, but there's a bedrock layer, and the river then moves within a thing called, within some sediments called alluvium. Alluvium are river moved sediments, or river deposited sediments. Now the alluvium is mobile, right? Like this is either just dirt or sand or clay, and the river can cut through, and what we see is the rivers are dynamic. They move all the time. Some slower than others, but the river can channel, where the water is actually flowing, can actually move back and forth within those alluvial sediments. But usually once it hits bedrock, it's not going to be moving any further. It will slowly wear away at that bedrock, but that will take a long time. So rivers are kind of oftentimes organized like this, where they have what we call the riverscape. Now the riverscape is the area in between the bank full height. Okay, so the bank full height is basically where is normal water level. Now if you go to a stream, this is relatively easy to see. It's like a well-defined cut channel, and then right along there is what we call the riparian zone, and how often the river floods will determine how big that riparian zone is. When the river does flood, it floods into this thing called a floodscape. Now the floodscape is will oftentimes determine where the whole river valley is, but you can have bigger floods that would flood outside of the normal river valley potentially. Yeah. So look at this picture here, right? Here is the riverscape, and this is bankful height. Basically, bankful height would be like if the water was right up here, maybe given the scale here, maybe an extra foot or so of water in this river. But this river is pretty much at big full height. Then we have the alluvial sediments right here. And then, you know, the floodscape is pretty much right, oops, sorry, right there, right? So this is the floodscape. All that portion between from here over to here, because you know, these trees are showing that the river probably never much floods above here, at least for any amount of time. Now, does this river have a floodscape? I mean, kind of, right? Maybe down here there's a tiny little floodplain here, but realistically it's not that much. When the river floods, it just gets a little deeper here in this situation. So these terms, you know, can be used, but sometimes they don't necessarily have a lot of meaning. So when you go to a river, you oftentimes don't want to talk about the east bank and the west bank, you know, if a river is flowing north or south, right? Because check this river out here. It's flowing this way, okay? And what we like to use is left bank and right bank, okay? Because right here we have the left bank. Now what you do is you basically stand in the river, look downstream, and then your left hand is the left bank and the right bank is on the right. So, you know, if you're here, this is always going to be the left bank, you know, even though, so here you're looking down and here you're looking up, but this side of the river is always the left bank, even though the left bank switches from the east and the west on, you know, on this map right here. So yeah, we should be using left and right bank. The thalweg then, what is that? That is the deepest point in cross section in the river. Now I know some other professors talk about the thalweg as the fastest point in the river, and the thalweg most of the time does have the fastest flowing water, but in this case the real definition of a thalweg is the deepest point in the cross section of the river, and you'll see that can change back and forth as the river is bending. The thalweg here it usually is on the outside of the river. There are certain situations where you can have a thalweg that doesn't have the fastest flowing water. Okay. The thing about rivers is that I like this quote that all generalizations are wrong, which in itself is a generalization. I realize that. But rivers are very weird in that, you know, each river is unique, and there's so many different types of rivers that go to so many different places all over the world. You can always find a river. If you make a generalization about a river, you're probably going to be wrong in some other place in the world. So all the things I'm going to list here are essentially wrong for a variety of reasons. So this is what we think about a river, right? Like a nice stream that starts in the glaciery mountains and travels down the mountains, gathers with other tributaries onto a flat plain and becomes a big river, and it flows out into the ocean on a big delta. Okay, there are some rivers that do that, but plenty don't. Okay, so this idea that all rivers flow to the sea is not true, right? There's plenty of rivers that are what we call endorheic. Endorheic rivers are ones that just dry up or flow into a big wetland. There's a bunch of rivers in Australia that just kind of flow into the middle of the continent, create a big wetland, and then they just dry up there. There's plenty of rivers in very arid areas that flow for a while, but then they just dry up and don't go anywhere. So all rivers do not flow to the ocean, to the sea. A river, there's a generalization that rivers increase in size as tributaries join. Rivers don't necessarily have to increase in size, right? If you're flowing through a very arid, let's say, area, let's say we have a river that's looking like this with a bunch of tributaries coming in, right? So we would expect, down here, there's probably more water flowing through. Now, for most rivers, this is probably true. But if this is a really, flowing through a desert, all along here, while this tributary does join, you're getting lots of evaporation. Here, 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 here. All along the river, you're getting evaporation. So if the river is long enough and you don't have a bunch of tributaries joining it, then the water might actually be decreasing as you go to the right, and there might be less water here, at point A than there was at point B, just because you've had more time for evaporation to occur. So not all rivers get bigger as tributaries are joining it. We oftentimes think of rivers as being steeper in headwaters because of this picture, right up here. There's plenty of rivers, think about a little tributary that is starting right there. Okay, is this steeper than it is here? What about a first order stream that starts right here? The headwaters of the stream would be right there. Does that mean that river is going to have steeper headwaters? And the answer is absolutely not. Okay, there's plenty of rivers that are not steeper in their headwaters. A lot of people say that there's a gradual slope in their lowlands, and the rivers go from an erosion zone, like it's eroding the mountain away, and then they're transferring sediments here, and then they're depositing sediments in the mouth of the river in the delta. And while that might be true that some rivers do that, not all of them do that. There's plenty of areas where there's just kind of like any stream that would start in a prairie is going to have a transfer zone just completely throughout the entirety of the river. Okay, so now I want to talk a little bit about channel patterns, and we can compare basically what a river looks like, okay? And channel patterns are kind of like big categories of rivers that look a certain way. And what's cool about these channel patterns is we assume that the ecology of, let's say, a meandering river, like a river that's like really going back and forth, okay? The ecology of the river in a meandering section should be similar to another meandering section, with either within the same watershed or the same river in a different later spot. We say that even though this anabranching or this pool section is very close to this meandering section, the function of the ecosystem should be more similar in another meandering section. Okay, so let's talk about these different channel patterns, but before I do that, I need to define a little bit about certain types of sediments that rivers are going through. Now, some rivers do just flow over bedrock here. That's what's going on up here in this top picture, right? The rivers can degrade down to flowing to the bedrock, but some of them are just naturally flowing over bedrock. Some rivers will go through colluvial sediments. Now, colluvial sediments are sediments that are not river deposited, but just like gravity deposited because they have like little landslides, and that's what's happening here. These are small scale colluvial fans where you just get little rock slides, and then you have these colluvial fans down here, where here are the big ones. But then, the question is, what is this right here? Is this a colluvial fan or an alluvial fan? When you have this river coming through here, that river is probably depositing most of those, so that would be an alluvial fan, where river deposited sediments. So we're gonna get to these patterns here soon, but what defines what pattern we get depends on three main things. There's other things that can determine it a little bit, but realistically, slope, discharge, and sediment load are the biggest things that are determining what type of channel pattern you have, whether you have a multi-channel or a single channel river. And so when we look at basically how big this substrate is, mean grain size of the riverbed. So do you have big rocks or do you have clay? And what's saying here is basically at higher discharge, you get more multi-thread channels. So multi-thread channel would be like a river that's looks something maybe like that, right? Where the flow of the river is going through that way. Whereas this single thread channel would be just like, you know, a meandering river like that. What this graph is showing is that grain size, how big that sediment is, and how much discharge there is flowing down the river has a big impact on what that river looks like. Then also discharge and the slope will have a big thing. So what we see is the more discharge you have and the bigger the sediments are, you're going to get a braided river. That's going to be looking like this river here. Intermediate, you'll get a meandering, and then an anastomosing river. We'll talk about that here in a second. So, what is a meandering river? This is a perfect example of a meandering river where we have, you know, the river winding back and forth through a low gradient plane. Meandering rivers are single channel and they usually have relatively fine sediments. These are rivers that are flowing through large alluvial plains. There's pretty low slope and the river course changes on what we call decadal scales, so like several decades, okay? And you can see that here there's all these little things called oxbow rivers, you know, right there, or oxbow lakes right there. The main channel of this river here is right here. Here's where the flowing river is, right? Oh, here, let me see if I can clear. This point right here is about ready to, it'll take just one little flood to be able to break through that area there, and this will then probably become a new oxbow, and the river will then just kind of flow through this direction here real soon. And in meandering rivers, this happens on like a decade scale. An anastomosing river. So this is a classic picture of an anastomosing river in Australia, I believe. Another name for this is anabranching. So anabranching. There we go. And it's multiple semi-permanent channels. These are basically, if you were to take a meandering river and give it a little bit less discharge and finer sediments, like really, really fine sediments like clays, you're going to get a anabranching or anastomosing river. And these channels are really changing on the century to multi-decadal scales. So like 60, 70, 100 years, somewhere in there, where, you know, the river might, the river bend here might cut off and eventually, you know, come over here to flow through here. But it's much more longer lived kind of channels. A constrained or constricted river. So think about a river that's going through a gorge, right? Oftentimes you have bedrock that's flowing through bedrock or natural valleys. But these rivers can also be created from levees, right? So when we put a dike or a levee along a stream, what we're essentially doing is we're creating it, changing. This example here is taking a meandering river and basically artificially constricting it. Oftentimes these rivers don't have any floodplain, and that can cause for really high velocities. So Floods are very dangerous in constrained rivers because since the water can't spread out, you're just basically putting more water through a narrow pipe, which makes the velocity get much bigger. Alright, the next river is a braided river. Braided rivers are really cool. I really like braided rivers. I think they just look great. This is a river in the Arctic, and these tiny little streams are changing all the time, and the water is just kind of flowing over this broad floodplain, and this river is just going to be moving around all the time. These are many temporary channels. The river can change on a daily, even hourly basis. We think this is in response to the slope. Oftentimes when we have really high discharge rivers that are in really steep areas, and also in really like big sediment areas, sediment size has to be really big, so gravel or sand, you get a braided river forming. This is a really harsh environment. As you can imagine, if you're a fish that is living in this little channel, if all of a sudden it gets cut off and the river now flows over here and there's no water flowing here, which happens all the time, you might be losing your habitat and have to swim all the way downstream, all the way over to here, and that it's just a really harsh environment for pretty much all organisms. The rivers is generally really shallow, highly changeable, and there's essentially no predictability. Alright, a straight river. The name kind of says it for itself. These are really difficult to find. This is an artificially straight river, as you can imagine. This is not. This is a canal. But this one is natural. I don't remember if this one is natural or not. But what we might think of as straight rivers are just meandering rivers at a given time, like it is meandering and changing a little bit, but looks straight for a while. Certainly you can find straight sections on like a meandering river, but I think what we're really trying to think about as straight river is for a decent amount of time. But we don't really think that this is a natural type of river. So if you look at this chart closely, and feel free to pause this video, but what you're seeing is there is a whole lot of that based on the channel pattern up here. There's a whole lot of ecosystem services that change depending on what type of pattern you have. And what we definitely see is braided rivers themselves are extremely harsh, so they don't have a lot of necessarily natural ecosystem benefits, and they're not really used much by humans because they don't it's hard to oops. How do I get off of this? Oh, that is frustrating. I'm sorry, everybody. Okay. It's hard to do recreation on a braided river because there's not really that many fish that are living in there. So we put like a lot of low values on these anthropogenic services, so human-related services. Whereas an anastomosing river and an anabranching river is really high, right? Like they have the most biodiversity, the most water storage, the most sediment storage, and they're really great to do recreation on because of the biodiversity. They have way more fish species and all sorts of stuff. So depending on what type of system we're looking at, each of these channel patterns will create rivers that have different services and provide different things for humans and also the nature.